Let's have a brief overview of hydrodynamic boundary layer. From fluid dynamics course, we know that, let's say, if we have a flat plate, and for a flow of Newtonian fluid over the leading edge of. So let's say we have this Newtonian fluid that is flowing over this flat surface with the u infinity, and here is the leading edge of this plate. When it starts to flow from fluid dynamics, we know there's gonna be a boundary layer forming over the flow. As we show by that one, we show the thickness of this boundary layer by delta, and this boundary layer indicates the change variation of velocity from zero. At the surface we have a zero velocity. This is u is zero as the slip condition. So the first layer has a zero velocity, and as we move into the fluid, the velocity increases till it reaches to the u infinity, or the bulk flow velocity. So we are gonna see such a velocity profile that it's zero at the solid surface, and then velocity keep increasing until it reaches, say here, at 0.99 u infinity. That's the place that we define this boundary layer. And if you connect the collection of these points that the velocity reach to 0.99% of u infinity, that's going to form our boundary layer, and here we have u infinity. Now, this boundary layer is the region close to the plate that the effect of solid wall on the fluid is confined. So and that's what we call it, hydrodynamic boundary layer. We show it with delta. Delta is a function of x. If define this one as the x-axis and y-axis, so delta is a function of x, and the thickness, this is the boundary. Delta shows the thickness of this hydrodynamic boundary layer. So delta is the thickness of boundary layer, and this thickness starts from y0, where velocity is 0, to the y that velocity is 0.99% of u infinity. Another property that we define here is the wall stress. So if I define here by this velocity distribution, if I find what is the slope, this slope is going to be du over dy, and from there we can define the shear stress tau s, which is mu u dy at y equal to 0. So this is the wall shear stress, which is the viscosity of the fluid times the velocity gradient at y equal to 0. Viscosity mu is the dynamic viscosity and that's the important fluid properties. In fluid mechanics, this velocity gradients becomes very important as it provides a basis for determining the local friction coefficient. And show it CFX. I just put X here as shows it's just changing in terms of the distance from the x0 or from the leading edge of this place. CFX is defined at tau s divided by 1 over 2 density of L fluid U infinity square, where rho is fluid density.